Okay, welcome to another modular math video here. This one was interesting to me because I was watching a video on the Make Noise Maths module. And the person was saying that exponential means fast and logarithmic means slow. And I was thinking, well, what? It's interesting that's why it just means that. Why wouldn't they just put fast and slow? So we've been looking at, there's also right in the middle of exponential and logarithmic is linear. And so why would they use these? We've been doing these functions since grade 9. If I grab one of the most basic lines, y equals x. I'm in Desmos here. I think you can see it up on the screen. There's y equals x. Actually, even before we do this, as we look around on Modular, there are these symbols in other places as well, not just on maths. You can notice it in a bunch of VCAs. There are exponential and linear lines on there as well. So it's good to know some of the math behind why these things are in there. Now, if I look, some people, I was thinking as I typed in y equals x, most people remember, because it is like pushed into our heads in high school, y equals mx plus b is the equation of a line. So if I wanted to do the same line in that slope y-intercept form, y equals 1x plus 0 gives me the exact same line. The blue, if I hide it, how can I hide it, is right over top of the red there. So maybe I'll get rid of the red altogether. There is y equals x, the most basic line. Direct relationship between y and x. I'm going to put in an exponential equation. I think maybe two. Actually, I'm going to use this one. I don't know that we do I don't even know that Desmos can do this. It's called the natural logarithm. Let me see. Oh, it did it. So there it is. E is a value kind of like pi, where pi is 3.14 and the decimal keeps on going forever. E is just another number. I want to say it's an E because it's Euler's number, and it's like the natural, it appears in natural situations like, I think, spirals and stuff like that. I could be wrong about that. Someone could correct me in the comments. But so I'm going to use E and to the x. There it is. Now, what is interesting about this is at 1, it should be at that 2.17. Let me just double check here. X equals 1, a quick little line. Look at that, 1 and 2.718. So that decimal would keep going on forever. Anyways, we don't need that stuff. There is our exponential. Let's do, on our calculators, we've got a log button, but also right near it there's a ln button. The ln button is the natural log. So let me see if this can do ln also. Ln x. Awesome. Super awesome. Okay, so here is, and now if we look at these three graphs that are on there, the blue, again, is our linear, the green is our exponential, and the black one here is our logarithmic one. Now, exponential, actually, first looking, may as well talk about exponential first. They were saying that is our fast. If we turn it to exponential, things are happening fast. Now, to me, what that means is it probably starts at 0. And if you look past 0, things start going up really fast. A lot of other applications are money. There are like bacteria in questions and things like that, exponential growth. Deal with this type of thing. Now, if you look over here, it's really slow to increase. Really slow. It's like barely increasing, but that is an upward increase here until all of a sudden it just starts really going up. Now, that's why it's used a lot in financial applications. If you have a credit card and you're not paying off your credit card, initially it's like, that's not too bad, 18%. I don't know if that a lot of the time credit cards have got a high percentage. If you pay them off right away, you don't even pay any interest on it. But if you don't pay off those credit cards, it's a little bit of a cost. It's a little bit of a cost. You continually don't pay off those credit cards, it's going to start skyrocketing on you next thing you know. Linear, we deal with situations almost like a lot of the ones that come up are the taxi cab problems or printing t-shirts, where what you're doing is you're paying a base fee for maybe the screen setup and then a cost per shirt after that. Or like in the taxi cab, right when you jump into a taxi, I don't know, people probably now do Ubers everywhere, but right when you used to jump into a taxi, they'd push a button and you'd owe a certain amount, and then it goes based upon the kilometers after that. Now, logarithm, if you notice this one starts really increasing quite quickly, but then it is a slow, gradual increase after that. So, where we use logarithms the most in high school is probably only in grade 12, and it is when we're trying to solve for when we're trying to solve for x up here. The logarithms give us a whole bunch of tools so that we can solve for that exponent. Now, I'm sure they do a bunch in advanced functions as well. Again, I don't know, I haven't done advanced functions for a long time, but it is a function, so you could move this thing and transform it around the screen the exact same way you would a quadratic or an exponential or any other function. So that's why they would look at it there. That is kind of a background basis for what we're going to see over here on the modular. This is Vails, another quad VCA, and what you might be able to see right at the top there is it's got those same exponential linear markings. So let's see what these are doing. I have got, you can see it in the side of the screen here, pulsar, sending the polycinematic a pulse, which is making that noise. It's coming into Vails. It's going into our oscilloscope. That's what we can see on the screen there. It's also coming up to this little out so we can hear what's happening also. Now, it's going into the top channel of Vails, and I have this knob turned all the way to linear. Right at the top I can hear what's happening. Now, I don't think that we're going to be able to see a linear or exponential function, but if we think of what is happening in those, and I'm going to turn this all the way down. So that does the same thing if you remember back from the other video where we were talking about the amplitude. Even though this isn't a sine wave and this is a wavetable, it's still doing the same idea. It's still the amplitude, so from the center to the highest point. Now, if I were to increase this at a very steady rate, what we would see is that it increases linear. I tried to increase it as steadily as possible, and it increased. Hopefully we can see on the graph, it kind of increases. If we look at that increase there, it's almost like a gradual slope. Now, what should happen with the exponential is it won't increase very much to start, and then all of a sudden it's gonna really jump. So let's see what we can do. So I'm gonna switch this around. I'll move my hand in a second. I've switched that around, so now it's full exponential. And I'm going to try and increase at a steady rate again, and we can see on the oscilloscope and hear what happens. Okay, I'm going to stop right there actually for a second. I am straight up. When I started working with veils, I had it straight up when it was on linear and we could hear something. So we're straight up and we still can't hear anything. So hopefully, assuming that I know what I'm talking about here, it should start to increase rapidly. Here it comes. Oh. Now look, I'm going to decrease a little bit. I am barely over halfway. And if we look at the oscilloscope, I maybe made it to 3 o'clock and we were off the screen. Definitely some redlining, some clipping happening. So that's what happens when we have an exponential. It is just going way up there. I'm actually quite interested. If we decrease the overall volume and think of that as the same spike, how high can we get? There you go. You want to be able to add some distortion and don't have a distortion module? There it is. Okay. We are now looking at the maths module. And this is the module that actually got me really thinking about the video where I watched how they were talking on this dial right here. There is the exponential side and then there's the logarithmic side. They even went as far as mentioning, so this is the fast side, this is the slow side, and right in the middle, I think it's on linear right now, right in the middle. And we kind of saw on that picture how linear, if we think of bending that exponential, we could bend it straight and it becomes a line. And then if we kept bending it, it would turn into the logarithmic. So it's kind of in this dial. We're bending that thing. This we won't be able to hear, so I've still got the polycinematic kind of droning in the background there from the previous ones. We will be able to see it though, so we can't see it yet. I'm going to turn on this cycle. There we go. Now, this is kind of like an ADSR. It is, except it doesn't have all the DS, or what do we have? It's got rise and fall, so I think it's our attack and our decay. Our decay can also kind of be like a sustain. So it's got two of them in here, and this is kind of what happens in between. So right now, if we look at the oscilloscope, it is increasing. We can see our attack there. Right now it's on its way down. It's kind of deleting the previous attack. But even the decay, or the fall in this one, is linear. So now we're on our rise. We can make it rise for longer. I just decrease the slope. We can make it, well, it's on its way down now. So we can adjust that however long or short that we want. Alright, see how steep that rise is. And we can adjust the fall too. I just made it super quick. So, there is that. Now, I'm going to adjust it so that it's a bit longer. And our attack is a bit longer. So that once I change it from linear, hopefully we'll be able to see. Now, an exponential is going to kind of curve up. Remember, it's got the slow start and then it increases quickly. So I'm going to go very hard into... There it is. Maybe I won't go quite as much so we can see it a bit better. There's our up and our down. And you can see they're kind of curved inward and curved down as it comes down. That's our exponential increase and decrease. And it does seem to go quite a bit quicker. It's missing the whole x less than 0 side of the curve, so it is just quickly going up and then quickly coming down. Let's look at the logarithmic one and see what happens on that side. So now it's looking like that logarithmic curve from y equals 0. It hits our peak and then it's doing one again in the other direction. So that is why that other video was calling the logarithmic one slow and the exponential one fast, is because it's actually only taking the, the top right quadrant, the first quadrant, where in exponential, it's already starting to shoot up. For logarithmic, it's already starting to slow down and level out at that point. There it is, some logarithmic, exponential, and linear functions. We go through linear functions again in grade 9 and 10. Exponential we probably slightly look at in 10, but then we look at them in 11 and 12. Logarithms might get introduced in grade 11, but we're probably seeing it in grade 12. All of it done right here on Modular. Most people don't even know about it. Don't even realize they're doing all this math right in here.